Hello everyone. This is the second video on the multiple choice questions of the paper Real Analysis, and I am introducing here the second chapter, Improper Integrals. So here are some key points. We just overlook through it. So first, fundamental theorem of calculus. If f is continuous on closed and bounded interval ab, and if f of x is equal to integration a to x f of t dt, then f dash of x is equal to f of x. We can restate this theorem by using the Riemann integrability of the function. So for this one, function is not necessarily should be continuous at each and every point of closed interval ab. Suppose it is continuous at a particular point x0 belongs to closed interval ab and f is Riemann integrable, then also we have f dash of x0 is equal to f of x0. Next one, before going to the second fundamental theorem of calculus, we have some simple theorems. If f dash of x is equal to 0 for each x belongs to closed interval ab, then f is constant function on closed interval ab. And secondly, if f dash of x is equal to g dash of x for each x belongs to closed interval ab, then f minus g is constant, or we may say f of x is equal to g of x plus c for each x belongs to closed interval ab. Now, what is the second fundamental theorem of calculus? If f is continuous on closed interval ab and if phi dash of x is equal to f of x, then integration a to b f of x dx is equal to phi of b minus phi of a. Let's go for example on this second fundamental theorem of calculus. So, evaluate by using the theorem integration 0 to 2 t plus 1 whole square dt. So, here f of x is x plus 1 whole square, which is a polynomial function defined on closed and bounded interval, hence it is continuous on closed interval 0 to. Now, by using the first fundamental theorem of calculus, phi dash of x is equal to f of x. So, phi of x is nothing but integration of f of x is nothing but t plus 1 whole cube by 3. So, using this second fundamental theorem, this integration is equal to phi of 2 minus phi of 0. Use this limit. So, phi of 2 is 9, phi of 0 is 1 by 3. So, it is 26 by 3. We go for mean value theorems for integrals. So, before that, let state one theorem. If f is continuous on closed interval ab and f of x is equal to integration a to x f of t dt, and if f of x is greater than 0, then f is strictly increasing on closed interval ab, and if f of x is less than 0, then f is strictly decreasing on closed interval ab. Let's go to the first mean value theorem for integrals. If f is continuous on closed interval ab, then there exists some c belongs to open interval ab such that integration a to b f of x dx is equal to f of c into b minus a. Similarly, in the second mean value theorem for integral, we have one more function g of x such that integration a to b f of x g of x dx is equal to f of c integration a to b g of x dx. Before going to improper integral, so we revise what is the proper integral. So, for proper integral, f is defined on closed and bounded interval ab and f is also bounded on the same interval. Then integration a to b f of x dx is said to be proper integral. So, integration 1 to 2 x square dx, here f of x is x square, which is bounded on this closed interval 1 to. Next one, sin x by x. So, when x tends to 0, sin x by x tends to 1. So, it is bounded on closed interval 0, 1. Next one, sin x, this function is also bounded and limits are also finite. So, are examples of proper integral. Next one. So, there are three types of improper integral. First one is first kind, second kind and third kind. So integration a to b f of x dx is said to be improper integral if a is equal to minus infinity or b is equal to infinity or both. Means at least one of the limits should be infinite or both can be infinite. Both limits can be infinite. Or f is unbounded at least one of the point of the closed interval ab. Okay, then if any of the case satisfies, then we say that it is a improper integral. But if it satisfies just first condition, that is if limits are infinite but function is bounded, then it is said to be improper integral of first kind. If it satisfies second condition, that is f is unbounded but limits are finite, then we say that it is improper integral of second kind. And if both conditions are satisfied, then it is said to be improper integral of third kind. Some examples of improper integral of first and second kind. So for the first kind, function should be bounded on closed interval ab and one or both limit should be infinite. So here the first example, function is 1 by x, so which is bounded in the interval 1 to infinity, and obviously one limit is infinite, okay, infinite, and in each case, and over here function 1 upon x square plus 1 is again bounded function in this interval. Over here function sin x divided by log x plus 1 is also bounded function in the interval 0 to infinity. Now improper integral of the second kind in which f is unbounded at least one of the point of closed interval ab and limits of integrations are finite. So these are example where limits are finite and function over here 1 upon x which is unbounded at lower limit x equal to 0. Next one 1 upon x plus 1 into x minus 1 is unbounded at x equal to minus 1 and plus 1. So at both limits. And in the third example, function is 1 upon x minus 3 is unbounded at x equal to 3 and 3 belongs to the interval 0, 4. Now some examples of improper integral of third kind. So integration is said to be improper integral of third kind if f of x is unbounded at least one of the point of closed interval ab and limits are infinite. See over here these are example where one of the limit or both limits are infinite, and see function in the first case sin x upon x square is unbounded at x equal to 0 which is a lower limit. Second one root x upon x minus 1 is unbounded at x equal to 1 which is again lower limit. And third one e raised to minus x divided by x square minus 1 is unbounded at x equal to plus or minus 1, and this plus or minus 1 belongs to the interval minus infinity infinity. We discuss what convergence of improper integral of first kind. So this is the improper integral of first kind, integration a to infinity f of x dx. It's said to be convergent if replace this infinity by b and take limit as b tends to infinity, and if this limit exists then we say that this improper integral of first kind is convergent. Otherwise it's said to be divergent. Similarly, this integration minus infinity to b f of x dx is said to be convergent if limit a tends to minus infinity integration a to b f of x dx exists and finite. Otherwise, this integral is divergent. Some examples on improper integral of first kind. First one, integration 1 to infinity dx upon x square. Over here, this upper limit is infinity, so we replace it by b and take limit as b tends to infinity. Find out integration, put the limits, take limit as b tends to infinity. Replacing over here b by infinity, we get here limit as 1, so which is a finite, so therefore this given integral is convergent. Next one, integration 0 to infinity e raised to minus x by 4 dx. Over here upper limit is infinite, so replace it by b, take limit as b tends to infinity, put the find integration, put the limits, and we get answer as 4, which is a finite. So therefore this given integral is convergent. Next one, strategies for testing convergence of improper integral of first kind. So how to test convergence given this improper integral? If upper limit is infinite, replace it by b and take limit as b tends to infinity. If limit exists, then it is convergent. If lower limit is minus infinity, replace it by a and take limit as a tends to minus infinity. If this limit exists, we say that this integral is convergent, otherwise divergent. And last one, if both limits are infinite, then we divide this integration at some point c, then we have integration minus infinity to c f of x dx plus integration c to infinity f of x dx. And for the first one, now as lower limit is minus infinity, replace this minus infinity by a and take limit as a tends to minus infinity of integration a to c f of x dx plus, now upper limit is infinity, replace it by b, take limit as b tends to infinity of integration c to b f of x dx. If both limits exist and finite, then we say that this given integral is convergent. Strategies for testing convergence of improper integral of second kind. So in the second kind, f of x is unbounded at least one point of the interval ab. Suppose f is unbounded at point x is equal to a, then we replace this a by d and take limit as d tends to a plus. Why over here it is plus? Because a is a lower limit at which function is unbounded. If it is upper limit, then we write in that case minus sign over here. Next one, again here f is unbounded at the upper limit. So in that case, replace this upper limit b by c and take limit as c tends to b minus. Minus is because it is upper limit of integration a to c f of x dx. Suppose the last case, f of x is unbounded at some x is equal to p, where p lies inside the interval ab. Then we split this integral into two parts, integration a to p f of x dx plus integration p to b f of x dx. For the first one, replace p by c and take limit c tends to p minus, because over here p is a upper limit, and in the second integral replace p by d and take limit as d tends to p plus integration d to b f of x dx. If both limits exist and finite, then we say that given integral is convergent, otherwise divergent. Some examples on improper integral of second kind. So integration 0 to 1 dx upon x raised to 1 by 3 is equal to, now this function is unbounded at x equal to 0. So replace this 0 by a, here should be a, and take limit as a tends to 0 plus integration a to 1 dx upon x raised to 1 by 3. Find the integration, put the limit, answer is 3 by 2, which is a finite, so hence given integral is convergent. Next one, integration 0 to 4 dx upon square root of 4 minus x. So here function is unbounded at x is equal to 4, that is at upper limit. So replace this 4 by b and take limit as b tends to 4 minus. Find the integration, replace b by 4 and answer is 4, which is a finite, so given integral is convergent. Next one, integration minus 2 to 2 dx upon x square. Now this here function is 1 upon x square, which is unbounded at x equal to 0, so split this integral at 0. So we have two integrals from this one, integration minus 2 to 0 1 upon x square into dx plus integration 0 to 2 1 upon x square into dx. Now consider suppose second integral, integration 0 to 2 dx upon x square. Now over here it is unbounded at x equal to 0. So replace this 0 by a and take limit as a tends to 0 plus of integration a to 2 dx upon x square. Find the integration, put the limit, and limit due to this a tends to 0 plus, so 1 by 0. So that's why we get over here infinity. So limit is infinite. So if one of the limit is infinite or one of the integral is divergent, then obviously this given integral will be divergent. Some convergent test for improper integral. So first test is for improper integral of first kind. Integration 1 to infinity dx upon x raised to p is convergent if p greater than 1, divergent if p less than and equal to 1. Now this is test for improper integral of second kind. Integration 0 to 1 dx upon x raised to p is convergent if p is less than 1 and divergent if p is greater than and equal to 1. So for p is equal to 1, both kind of improper integrals are divergent. And last test, integration 0 to infinity dx upon e raised to x converges if a greater than 0 and diverges if a is less than and equal to 0. What is absolute and conditional convergence of integral? Suppose f is Riemann integrable, and if integration a to infinity mod of f of x dx converges, then we say that integration a to infinity f of x dx converges absolutely. Otherwise, we say that integration a to infinity f of x dx is conditionally convergent. So here one typical example, integration 1 to infinity sin x by x dx is conditionally convergent. Instead of sin x we may have cos x too. So and second example, integration 1 to infinity sin x upon x square into dx is absolutely convergent. Okay, because we are going to write this integration, if I put over modulus, then integration 1 to infinity mod of sin x by x square into dx is less than or equal to, since mod sin x is less than or equal to 1, so is less than or equal to integration 1 to infinity dx upon x square. And compare with the p integral test, integration 1 to infinity dx upon x square is convergent because p is equal to 2 greater than 1, so it is convergent. So by comparison test, this one is smaller than integration 1 to infinity dx upon x square. So by comparison test, this is also convergent. And since its modulus is convergent, so it is absolutely convergent. Okay. Next one. If integration a to infinity f of x dx converges absolutely, then integration a to infinity f of x dx is convergent. So when any integral converges absolutely, then the integral is also convergent. Now comparison test. So if f of x is greater than or equal to g of x and integration a to infinity f of x dx is convergent, then integration a to infinity g of x dx is also convergent. And in the same way, if f of x is greater than or equal to g of x and integration a to infinity g of x dx diverges, then integration a to infinity f of x dx also diverges. Now we are going to use here p integral test and comparison test to solve the examples or to test the convergence of integrals. Suppose this is the given integral, integration 1 to infinity dx upon x square plus x plus 1. So this is the function. Now its denominator is x square plus x plus 1. Since x is positive, x is greater than or equal to 1, so we may say x square plus x plus 1 is greater than x square. Taking reciprocal, 1 upon x square plus x plus 1 is less than 1 upon x square. Take integration on both sides from 1 to b, okay, and then take limit as b tends to infinity. So we get this one. Now by p integral test, this is the improper integral of first kind, and by p integral test for the first kind, here p is equal to 2, which is greater than 1, hence it is convergent, and it is smaller than this one, so by comparison test this is also convergent. So therefore given integral is convergent. Next one, to check convergence of this integration 2 to infinity dx upon log x. Okay, so we compare this log x with x. So we know that log x is always less than x for all x greater than 2. Now if I take reciprocal, 1 upon x is less than 1 upon log of x. So take integration on both sides from 2 to b. Take limit as b tends to infinity. So we have integration 2 to infinity dx upon x less than or equal to integration 2 to infinity dx upon log of x. So now dx upon x, here p is equal to 1, and it is improper integral of first kind. When p is equal to 1, both kind of improper integral, either first kind or second kind, they are divergent. So it is divergent, and this one is greater than this integral. Okay, this given integral is greater than this integral, which is a divergent. Hence this given integral by comparison test it also diverges to infinity. So last part, Cauchy's principal value. So Cauchy's principal value of the integral minus infinity to infinity f of x dx is defined to be limit s tends to infinity integration minus s to s f of x dx. One more important result, if integration minus infinity to infinity f of x dx converges to a, then this Cauchy's principal value is also equal to a. So if integral converges to a, Cauchy's principal value is also a, but converse is not true. Cauchy's principal value may exist even if integral diverges. One example, so this is the given integral, and to find Cauchy's principal value, so use the definition limit when s tends to infinity integration minus s to s x dx. So that is equal to, now over here we may split here this integration into two parts. So minus s to 0 x dx plus integration 0 to s x dx. Now observe here, function f of x is equal to x is a odd function. Okay, when function is said to be odd, if f of minus x is equal to minus of f of x. So when it is odd function, then obviously we get here sum of two integrals will be 0. So limit of 0 is equal to 0. How to find Cauchy's principal value when function is unbounded at some point c which belongs to closed interval ab. In that case, we split here integral minus infinity to infinity at the point x is equal to c. Suppose integral is of from a to b, then we may write limit epsilon tends to 0 plus of integration a to c minus epsilon of f plus integration c plus epsilon to b of f. Let's go to the multiple choice questions on the topic. If f is continuous on closed and bounded interval ab and f dash of x is equal to f of x, directly use over here first fundamental theorem of calculus, and using it we have the option C, f of x is equal to integration a to x f of t dt. So answer is C. If f is continuous on closed interval ab and f of x is greater than 0, where f of x is equal to integration a to x f of t dt, then here are the option, and as f of x is greater than 0, so f is strictly increasing. So answer is C. Next one, if f is continuous on closed interval ab, then there exists c belongs to open interval ab such that integration a to b f of x dx is equal to, use here mean value theorem first mean value theorem, and using it we get over here it is f of c into b minus a. So answer is C. Next one, if f of x is integration 0 to x square root of t plus t raised to 6 dt, then f dash of 2 is equal to. Here we use first fundamental theorem of calculus, and f dash of x is nothing but square root of x plus x raised to 6, and f dash of 2 replace x by 2. So we have it is root 66. Answer is A. If f of x is equal to integration 0 to x square root of 1 plus t dt, then f dash of 3 is equal to. Again use this same theorem, f dash of x is equal to root 1 plus x, f dash of 3 is equal to square root of 1 plus 3 is 2, and answer is C. By using p integral test, integration 1 to infinity dx upon x raised to p converges if, now as it is a improper integral of first kind, so therefore it converges if p is greater than 1. So answer is A. By using p integral test, integration 0 to 1 dx upon x raised to p converges if, now it is improper integral of second kind, so it converges if p is less than 1. So answer is C. Integration 1 to 2 x plus 1 whole square dx is, observe here limits are finite, so it cannot be of first kind, can be of second kind, but here function x plus 1 whole square is a polynomial function, hence it is bounded, it is a bounded as well as limit finite, so it is a proper integral, not improper integral. Answer is D. Which one of the following is not improper integral? It is not improper integral, so first of all limit should be finite. Yes, in all cases limits are finite, and function should be bounded. So over here 1 by x is unbounded at 0, so this cannot be. 1 upon x is unbounded at 0, and 0 is not member of the interval 1 2. So obviously answer is B. Over here x minus 2 whole cube, so that's why this function 1 upon x minus 2 whole cube is unbounded at x equal to 2, that is upper limit. Over here it is unbounded at x is equal to 1, which is a lower limit. So answer is B. Which of the following is improper integral of first kind? So for first kind, one of the limits should be infinite. So this 3 can be answer. So and function should be bounded. So 1 upon x, which is bounded in the interval 1 to infinity. Here 1 upon x is unbounded at 0, and over here 1 upon x is unbounded at 0, and 0 is in minus infinity to infinity. So answer obviously is B. Next one, which of the following is improper integral of second kind? So first condition is that limit should be finite. Yes, limits finite. So A and so over here function 1 upon x plus 1 is unbounded at x equal to minus 1. It is a lower limit. Okay, so this first option is a improper integral of second kind. Which of the following is improper integral of third kind? So integral is of third kind if one of the limit is infinite and function should be unbounded. So here are two options where limit is infinite and 1 upon x is unbounded at x equal to 0. So this cannot be. So this is the option, correct option. So answer is C. Which one of the following integral is convergent? So integration 1 to infinity dx upon x square. So it is a integral, improper integral of first kind. It is convergent when p greater than 1. So here p is equal to 2, which is greater than 1. So correct option is A. We may check for rest of the two. Over here p is equal to minus 2, not greater than 1. Here p is equal to 1 half, not greater than 1. Here p equal to minus 1 half, not greater than 1. So correct answer is option A. which one of the following integral is divergent? So over here integration 0 to 1, all these are improper integral of second kind. So function over here apply PCL test. So p is equal to 2 greater than 1, so it is divergent. So correct option is A. Over here observe, here p is equal to minus 2. If I shift the term in the denominator, p is equal to minus 2 and it's not greater than 1. P is equal to 1/2, not greater than 1. P equal to minus 1/2, not greater than 1. So correct option is A. Which one of the following improper integral is divergent? All are improper integral of first kind. So which one is divergent? When p is equal to 1 or less than 1. So here p greater than 1. If I shift the term in the denominator, p greater than 1, so these are convergent. Over here equal to 1, p is equal to 1, so this is divergent, and over here p is again x raised to 3 by 2, so greater than 1, it is convergent. So correct option is C. Next one, integration 0 to infinity dx upon x square is now convergent, conditionally convergent, divergent, and can't say about convergence. So this integration 0 to infinity dx upon x square is unbounded at x equal to 0 and one limit is infinite. Okay, so it is improper integral of third kind. So we divide this integral into two integrals so that we get one of improper integral of first kind and one of second kind. This is of first kind, this is of second kind. This is the improper integral of second kind, and with p integral test, p is equal to 2 and greater than 1. So that's why it is a divergent. And this is p is equal to 2 and greater than 1. So it is a convergent. This is convergent, but this one is divergent. So obviously this given integral is divergent. So option is C. Which of the following is absolutely convergent integral? So this sin x upon x, obviously it is conditional convergent. Integration cos x upon x, conditionally convergent. Integration x square into cos x, if I shift x square in the denominator, okay, so I'll have x raised to minus 2 in the denominator. So I have integration 1 to infinity cos x upon x raised to minus 2. Now one more thing, when any integral is said to be absolutely convergent, if I put over a modulus and still it is convergent, then I can say it is absolutely convergent. If I put modulus over here, then we have mod of cos x divided by x raised to minus 2. It is less than or equal to 1 upon x raised to minus 2. Okay. Now integration 1 to infinity dx upon x raised to minus 2, where p is equal to minus 2 and it's less than 1, so it is a divergent. Okay, so it is also divergent. Now what about this one? Here if I put modulus, it is less than or equal to integration 1 to infinity dx upon x square. Now with p integral test, here p is equal to 2, so greater than 1, so it is a convergent. So after putting modulus and by comparison test, after putting modulus, this integral is also convergent. So therefore it is absolutely convergent. Correct option is D. Integration 1 to infinity cos x upon x square into dx is, options are absolutely convergent, conditionally convergent, divergent, and doubtful. So obviously here again put modulus and apply comparison test, and we get integration 1 to infinity dx upon x square, and which is a convergent, and so that therefore by comparison test given integral is convergent, so it is absolutely convergent. So correct option is A. Which of the following is conditionally convergent integral? Obviously integration 1 to infinity cos x upon x dx is conditionally convergent, so option is A. Integration 1 to infinity f of x dx is conditionally convergent if, when it is conditionally convergent, after putting modulus to f of x, it should be convergent. Okay, so correct option is that after. Next one, integration 1 to infinity f of x dx is conditionally convergent if, when it is conditional convergent, after putting modulus to f of x, this integral should not be convergent. So this should not be convergent. So first option is not correct. Second one, it is not convergent, but integration 1 to infinity f of x dx is convergent. Yes, B is a correct option. So answer is B. Next one, integration 1 to infinity f of x dx is conditionally convergent, then which of the following is not correct? Okay, so when it is not, for conditionally convergent, modulus, after putting modulus to this f of x in the integral, and that should not be convergent. Okay, so when it is not correct, when it is convergent after putting modulus to f of x, and if that integral is convergent, then it is not correct. So integration a to infinity mod of f of x dx is convergent is not correct. So correct option is B. Let a is equal to integration 0 to 1 sin x upon root x dx and b is equal to integration 1 to infinity sin x upon x dx. Then a and b both converges absolutely. A converges absolutely, b and b converges conditionally. A converges conditionally, b converges absolutely, and a and b both converges conditionally. So we go to the integral a. So it is integration 0 to 1. Consider if I put modulus over here to check convergence. So it is less than or equal to integration 0 to 1 dx upon root x. By p integral test, here x raised to 1/2. So p is equal to 1/2, which is less than 1. So it is a convergent, because it is improper integral of second kind. So it is a convergent. Hence it converges. After putting modulus, we get convergent. So hence it converges absolutely. Now what about B? Now B is a typical example of conditionally convergent integral. So it is a conditional convergent. This is a absolute convergent. So A converges absolutely and B converges conditionally. So correct option is B. Next one, CPV of A is equal to integration minus infinity to infinity dx upon x and B is equal to integration minus infinity to infinity x dx. So R equal to 0 does not exist. CPV of A equal to 0 and CPV of B does not exist. CPV of B equal to 0 and CPV of A does not exist. Now here both A and B, okay, having the function in the integral 1 upon x and x are the odd function. Okay, so when functions are odd, obviously CPV is equal to 0. See, look at how to find CPV. Integration minus s to s dx upon x. Here limit we replace infinity by minus s to s, and finally we will take limit when s tends to infinity. So that is equal to integration minus s to 0 dx upon x plus integration 0 to s dx upon s. Okay, we change the limit lower to upper. So that's why we have minus sign, 0 to minus s dx by x, second as it is, and now replace x by minus x. So when x is equal to minus x, dx is equal to minus dx, and when x tends to minus s, minus x tends to s. So this limit is also s. So we have minus of integration 0 to s dx upon x plus integration 0 to s dx upon x, and sum is 0. So limit as s tends to 0, infinity of 0 is equal to 0. So therefore CPV of this A is equal to 0. Similarly we can prove for B also 0. Answer is A. Next one, CPV of integration minus 1 to 1 dx upon mod x is equal to, options are 0, 1, minus 1 does not exist. Integration minus 1 to 1 dx upon mod x we may split where the function is unbounded, that is 0. So integration minus 1 to 0 dx upon mod x plus integration 0 to 1 dx upon mod x. Now over here x is negative. So when x is negative, mod x is equal to minus x. when x is positive, mod x is equal to x. So we shift this minus sign outside, and because of minus sign, this we can change this limit -1, which is lower limit, to upper. So we have integration 0 to 1 dx upon x. So 2 times same term. So we have 2 times integration 0 to 1 dx upon x. 2 into limit when epsilon tends to 0, integration epsilon to 1 dx upon x. So that is equal to 2 into limit epsilon tends to 0 minus log of epsilon. Obviously, when epsilon is equal to 0, so this log of 0 does not exist. So therefore, here CPV of this integral does not exist. Next one. CPV of integration minus infinity to infinity 1 plus x divided by 1 plus x square dx is, to find CPV of the integral which is given by limit s tends to infinity integration minus s to s 1 plus x divided by 1 plus x square into dx. We split here at 0. So first integral is minus s to 0 and second one 0 to s. Now replace x by minus x in the first integral. So we have when x is equal to minus x, then dx, that will be minus dx. So over here minus x, 1 minus x divided by 1 plus minus x square is x square, and minus dx. So we have minus sign over here. So we may change here limit, okay, using it 0 to x. When x is equal to minus s, obviously minus x is equal to s. So that's why we have this s. Okay. So both integrals have the same limit. So we find the sum. So it is nothing but 1 minus x, 1 plus x, minus x plus x get cancelled. So 1 plus 1 is 2. So we have 2 integration 0 to s dx divided by 1 plus x square. Integration is tan inverse of x, and so after putting limit, tan inverse of s minus tan inverse of 0. So this is 0 tan inverse of s, and when s tends to infinity, it gives us tan inverse of infinity is nothing but pi by 2. So pi by 2 into 2. So that gives us pi. So correct answer option is C. If CPV of integration minus infinity to infinity f of x dx is equal to a, then integration minus infinity to infinity f of x dx is, options are converges to a, is divergent, is convergent, and converges to some finite, and may not convergent. We know that if integral converges, then converges to a, then CPV is equal to a. But if CPV is equal to a, integral may or may not convergent. So correct option is D. So thank you.